Hello, everyone. So our next speaker is Stefan Bernal, and he will be talking about lifting your speed limits with Cython.
So hi, can you hear me well? It's okay, right? Okay. Welcome to my talk. This is probably the biggest hall I've ever taught in, so I'm really happy to be here at FOSDEM. The first time at FOSDEM, so. So my name is Stefan Bernal. I regularly give talks at Python conferences. So this is my it's my first non-Python conference in quite a while, in years. So the talk will be on Cython, on the Cython compiler, so Python-related topic. I'll have a quick poll first. How many of you are regular Python users? Okay, pretty much the majority. How many of you have used Cython before? Well, some of you. Okay. How many are in the big data, scientific computing, this kind of area, so doing data processing in some way? Okay, cool. That's about a bit less than half of you, I think. Okay, cool. So I'll get started with my talk. First of all, a bit more background on myself. So I'm a core developer of Cython. Have been that since the early beginning. So we started the project in 2007. Actually, as a fork of a different project at the time, which no longer really exists. So this is kind of the thing you want to use today. So that was it's more than 10 years already. So we had our 10th anniversary last year. Quite a while for working on an open source project, but it's still alive and kicking, and it's doing very well. I'm giving trainings and consulting on Cython. So if you have any interest in using it, better than you currently do, or starting using it, please contact me. I can help you with that. But most of the time during the week, I'm actually working for a company called TrustYou. And at TrustYou, this is what we do. So what you can say you're looking for a hotel in Google, and it's going to give you a lot of information about that hotel, including a rating. Okay, so you give something like this is a 4-star hotel, 3.9 out of 5, something like that. And if you click around a bit in what they show, they'll eventually tell you that this rating is actually coming from us. So what we do is we collect hotel reviews, so actually written text, from throughout the internet, various places, that's from booking portals, so reservation sites, but also sites that collect reviews like Holiday Check or TripAdvisor, for example. So we get those, collect them, and then do a huge amount of data processing on them. Like really at global scale, so we collect them globally, analyze the data, analyze the actual text that people write, so we do NLP, language processing, and then do statistics on that. And so Google's only one of our clients. What we actually do is we sell these statistics and this information back to the hotels. And then we can tell them stuff like, in comparison to the hotel next door, you could improve your ratings by 10% if you keep your rooms cleaner, or stuff like that, or if you renovate your pool, for example. So that's what we do, and this is how we do it. So this is how we show all this data to hotels and how they can use this data to improve their own performance and get guest feedback in a unified and well-established way. And down there, you can see this is really big data. So we get something like 3 million new reviews every week, and we have a huge bunch of reviews that we're sitting on that we can do data processing on. So why do I tell you all this? Well, we do all of this in Python, right? So why do we use Python? It really works for us. It's a great programming language, really. It's very versatile. It's a very pragmatic language. It's concise. It's readable. So it's very nice, and has a great community, which is very diverse. It's friendly. It's very helpful. Things tend to be well documented, and if they're not, there's a huge bunch of stuff on Stack Overflow, for example, where you can look stuff up, where you can ask questions. Apart from that, it has an excellent set of libraries and tools that you can use for data processing. So it's really a great environment and ecosystem that we can build on. It has a great ecosystem for big data processing, NLP, for building web services, for automation, for all the data flow processing that we do, for testing, for all that. And many of these tools are very well integrated, which is also cool. So it's really not just like you have one great tool and another one there. It's a great ecosystem that we can work on. And why is that the case? Because all the data processing is usually based on NumPy, so there's a data structure that all these tools can build on, like SciPy, like scikit-learn, pandas for data analysis. All of these tools are well integrated via the data layer. And it's not only the data layer that integrates them, and now we come to Cython, because Cython is a great way to integrate code. Okay? So the data ecosystem works that well because many of these tools use NumPy as their data layer, and a surprisingly large number of these tools that we use integrate external libraries, integrate native code via Cython. Why Cython? Well, it's actually the fastest way to integrate native code. I'm standing here, I give the talk, so I can say that. It's production proven, it's actually widely used, and it's really all about getting stuff done. Okay, it's a pragmatic programming language. It helps you keep your focus on functionality rather than having to care about a lot of boilerplate everywhere. And it allows you to move freely between Python and C or C++, which is something that makes it a really unique programming language at that level. You can write code in it that is as Pythonic as you want and as native as you need it. And you'll see examples for that in a couple of minutes. Basically, we write the C code that you don't have to write. We write C so you don't have to. Okay, here's a demo. Who knows the Jupyter Notebook or IPython Notebook? Actually, not so many. You should be using it. It's great. It's a wonderful tool. What it gives you is a little web server that you run, and then gives you a web interface. So it runs in your browser and allows you to program in your browser, run code, and do stuff like data analysis and program it in a very interactive way. So you type a line, you get feedback, and you can visualize data through it. So it has direct output for graphs, for example. Lots of tools support it. There are tools that do interactive, provide an interactive way to visualize data and to move stuff around and try stuff out and that. So it's a really great tool. So remember that name, Jupyter Notebook. So what I'm doing here is I'm using it for my presentation. There are actual presentation tools also for it. So I could give you something like swipe here and there and do stuff, but I actually prefer that way. So in order to make the Jupyter Notebook run with Cython, all you have to do is load X Cython, then it imports Cython, and it just knows what Cython is and has Cython support in it. And then just to give you an idea about the environment I'm working in here, you'll know that the core developer is talking to you when they're using some pre-release alpha version in a live demo. Okay, so let's see how that goes for me. I'm using NumPy, using Cython, Python 3.6, kind of a recent GCC version. more or less. Okay, bit of boilerplate here. Quick intro to Cython. This is normal Python code. So what I do is I take the Python math module and import the sign function from it, and I call it, and I get the output from it. Okay? So that's sign of 5. And now all I have to do in order to use Cython with that is I tell the Jupyter Notebook, this is a Cython compiled cell. So this is no longer interpreted by Python. Please make it run in Cython for me. And then what it does is it compiles it for me in the background, imports the module, and runs it. Okay? So this is now compiled code, a compiled module. And so what Cython does for me is it compiles the Python code to C, also C++ if you want, but generally C, so into native code. Okay, so what the Jupyter Notebook does here is it runs Cython to generate the C file for me, and then starts the C compiler in the back to generate a native extension module, a shared module that then gets imported by Python. Okay, clear so far? That's the general build process. Now, since this is translated into C, what I can do now is, instead of using the Python math module, which requires me to do a Python call and has some sort of checking here and there and some special casing and more than I would require, generally require to, say, sign of 5, I can use the libc math support. And this is how I do it. I say C import, so that's a static import in Cython, C import libc math, and then I take the sign function from it, and here I just assign it to a Python variable. And what that does is, it auto wraps it for me, so I get a Python function, which now internally calls the sign function. And I can use that from Python, and then it says that's the same value as before. This is sign of 5. Okay? So what did I do here? I made Cython auto wrap a C function for me to make it callable from Python. Okay? That's a bit boring from the sign function because there's Python support for it. It gets a bit more interesting as soon as I do not only call some C function but do stuff along the way. So I want to have an interface. I want to have a function in Python that I can use, and it internally uses the sign function. But I could say sign of 5. But maybe I want to have sign of x squared or something. So there's a bit more computation involved now. And in order to drop this from a Python computation, so I could say sign of x squared, okay, fine, in Python, sure. I can do the same in C, and it's actually faster to evaluate in C, right? Because there's just, the processor sees what it does, it's no longer interpreted, so it's native code running. So what I can do here is I write my own little Python function. So this is now a bit of extended syntax that we have in Cython. I can say the argument that I pass in, is in fact a C double. So I'm typing my input argument here, my variables, and then I call the sign function in there. And that's essentially the same thing as here. So here above I get auto wrapping, and down there I'm spelling out the function. Okay, so here I'm writing a Python function that calls C internally and still gives the same result. And now if I want to do sign of x squared, then I just spell that out. And just to see the difference, I will actually ask Cython to tell me what kind of C code it generated for me. So for the function I just wrote, when I don't just say %% Cython, so the Cython cell, when I say Cython minus A for annotation, then it spits out an HTML snippet for me, which the Jupyter Notebook can display for me here, which contains my source code and tells me how Cython interpreted that source code for me, how the compiler saw it. And you see there are a couple of shades of yellow in there. And these shades of yellow tell me how much Python interaction there is going on. So whenever objects are being treated in some way, the more object operation there are, the darker the yellow gets. Okay? So there's obviously a lot of Python interaction, and this is the C code here, that generated going on in the signature, because the signature actually has to convert some Python input argument that comes in, some object, into the C double that I declared. So it has to take some object, unpack it into a C double, do that conversion, do some general argument handling in the way that Python semantics works. So this is the place where the Python call semantics is mapped to a C call semantic. Okay? There's a lot of object and operation going on here. And then the next line is just a line that calls the sign function. You can see that here. It just says sign of x in the C code. Okay? So this is really a plain C operation. And since this is a Python function, the return argument then also has to be an object again. So this function does object to C conversion on the way in and C to object conversion on the way out. And you can see that here. So the result of sign of x is converted using a C API function of Python into a Python float object. Okay? Okay. And that's pretty much all there is to it. Now when I want to do sign of x squared, here's a Cythonic way of doing it. I'm squaring x, and then I call sign of x squared. And again, when I look at the result here, Cython minus a gives me down here, this is a pure C operation, so no object operations going on here. X times x is the square, and then sign of the square, and convert it into an object again. And Cython does all these things automatically for me, so you don't actually see them in the code. It's just the type system of Cython, which mixes Python and C. And that allows it to see where object conversions are going on, where native code can be generated from your code, and where Python operations are needed. And Cython does all this internally. So by default, it's Python. You can drop Python code in there. It compiles into C, but it's Python, it has Python semantics. And whenever I say, I know better, you don't need an arbitrary object here. You can use a C int, a C double, some native data type. Then the compiler can say, okay, you leave in Python semantics, you get into C semantics here, which are faster, but a bit different, and it automatically does it for me. So it generates different code when I say, but the data structure or the data type is different here. Okay, is that clear? Any questions on that? High level something? Okay. Okay, so this is generally how the language works. It mixes Python and C, and you just, normal Cython code just looks like that, but you always jump somewhere between Python operations and C operations, or C++ operations, back and forth, and it just chains nicely. This is how you would do memory handling in C. How many of you actually have some kind of C knowledge? Quite a number. That's 2/3 maybe? Okay. Was that more than the Python? I think the Python background was a bit bigger even, but there's not a big difference. Interesting. So this is the right talk for you. C memory handling, malloc and free, you probably know those. And you can just use them in the same way in Cython. So the Cython code doing a malloc. If the malloc failed, then here I do raise memory error. Isn't that great? I mean, this is totally C-ish code. Like you do malloc, you do free, and then right in the middle you see raise memory error. Wonderful, right? I love that. And it works. That's how you do memory error handling in Cython, right? The same way as you do in Python. So it's much nicer than in C, where you'd have to say, whoa, what do I do now? What do I have to clean up? You do try finally, right? Try finally. Catch an error, handle the exception somehow. It's just as safe as Python. Okay. So in the end, I do call free, and then here I do a bit of memory processing. You see that I'm using a pointer, I'm using slicing on a pointer, so slice assignment here. So this is normal Python syntax, just with C data types. Okay, can I make this a bit smaller? Is that size okay, or is that too small? Too small for anyone? Okay, because there's a bit of more code coming now. Using third-party libraries. This is, how many of you know Lua as a programming language? Yeah, quite a number. So Lua is also, by default, an interpreted language. So there's a runtime for it. There's also a JIT compiler, LuaJIT, which I'm actually using here. And now what I'm doing is I'm writing a little Lua interpreter that takes a string, a bit of Lua code, puts it into Lua, executes it there, and then returns the result of the processing back into Python. Okay? And I'm implementing that in Cython. So the first thing you have to do, you've seen this cimport math, libc math before. That's the simple way because Cython comes with pre-declarations for libc. So most of what you would use in libc can just simply be C imported from Cython code. For external libraries, Cython does not ship declarations, and you need to copy them together from the header files. So what I did here is I took the stuff that I needed from the Lua header file, create a new interpreter, clean it up, load some code into it. Lua is a stack machine, so I'm doing some stack operations to get data in and out of Lua, and call a function in Lua. So that's basically the functionality that I need. Copied those from the header file into the declarations to make Cython aware of the C API that I'm working with. So now Cython understands the C API, it knows what functions I can use, what data goes in and out, and I can now just call them. So what I do is I write a Python function, run Lua, and which receives the code. First thing I have to do, Lua doesn't have Unicode support, so I convert the code into UTF-8 if necessary. Then I create a Lua runtime. If that fails, I can look up in the documentation that the probable reason for that is not enough memory. So I raise a memory error if that fails. And then once the Lua runtime is created, I wrap all the rest in a try finally statement because I know in the end I have to close the Lua runtime to free the resources. Okay? So resource management using try finally here. And the first thing I do is I take the Lua code, load it into the Lua runtime. If that fails, it's probably a syntax error, so I raise a syntax error. What I get back is then kind of a Lua code object, something I can call. So the next thing is I execute the code in Lua. If that fails, I raise a runtime error, probably some, something went wrong, some input wrong or something. And then just for simplicity, what I'm expecting back here from that code is some number output. And I convert that number into a Python object here, explicitly because I have to extract the number from the Lua runtime. It's actually a float, a double, in a C double, what I get back, and then Cython converts that C double into a Python object again. Okay? So that's what happens here. In the end, some cleanup, clear the stack, close the runtime, that's it. So that's all I need to execute code in Lua. Okay? As I said, it's a Python function, so I can call it from Python now. When I execute this, then it gets compiled. It actually uses LuaJIT in this case, which I'm configuring here. So I'm telling the build, please look for Lua in this directory. Use this library to link against, and that's all I need to do to link in Lua and talk to Lua. Okay, so here's some Lua code. Where? Here. Lua implementation of Fibonacci. So I'm executing that code here. Fibonacci of 10 is 55. Probably going to believe that. And now I can see how fast that runs. And it takes, so Fibonacci 24 takes about 2 milliseconds to execute in Luajit. Okay? So this is all the code I needed to write in Cython to talk to an external C library, to use a separate runtime. And as you can see, I mixed Python code with C calls completely freely. Right? So I'm saying, raise an error, raise an exception, a Python exception if something fails, call this function and pass some Python data into it. And Cython does all the rest for me, because Cython understands, this expects a character pointer in C, and I'm getting a string in. Okay, I can convert that, right? I can unpack the string and pass the data. And that's something that Cython cares about, and that I don't need to care about when I write my code. Really nice. Okay, how much time is left? 25. Okay, cool. So here's a real-world example of writing some data processing code in Cython. Okay, everyone likes Texas, right? So this is an example that everyone understands. What I did here is I actually stole this example from some Australian guy, Caleb Hetting, who gave a talk, a Cython talk, interestingly enough, at the PyCon Australia 2 years ago. Really nice talk. And so here's the example he gave. I really like that because it shows a couple of interesting properties. So I looked up the average income in Germany, which is where I come from. And this is more or less it. And I looked up the number of earners that we have, which is 44 million, sorry. So the average income for those over the year is 44,000, more or less. That was in 2016. Now the question is, what's the average tax rate that everyone pays? How many taxes do we pay? And I actually tried to back these numbers by real data somehow, and didn't find any. There was, well, I didn't search very deeply, but I guess it's just for privacy reasons that they don't publish accurate data on this. But that's the average numbers that they give. And so to get actual data, to calculate the tax rate, I'll just make up some alternative facts here. And so just to show you what data I'm using, I'm plotting a graph of the income distribution, which in this case is just a log normal distribution. Okay? It's more or less what you would expect from the income distribution. It's not entirely incorrect, and you can see the minimum and the maximum here, which are also not completely unrealistic. And I just chose the values here, the setup for the log normal distribution, so that the average is also more or less correct, as expected. Okay, so that's my data. And let's calculate everyone's taxes. When you look up the income tax for Germany, in Wikipedia, what it gives you is an Excel implementation, right? Isn't that wonderful? And this is how it looks like. It's even in German, so it's a German Excel, right? It's not if this, then that. It's like wenn, and like formulas, and glorious. I love it. It's a German income tax, so it's okay if it's in German, right? You probably wouldn't care about the exact details, but this is the formula how we can calculate our income tax. Basically what it does is, if the income is greater than this, then this is the formula for it, and if it's, so there are like certain boundaries in which there's a gradual increase in income tax, something like that. So spelled out in Python, I think this is much more readable. This is what it is. So same formula, exact same thing, just in Python. And then to calculate the average income, I take the sum of all incomes divided by the len of incomes, obviously, and the average tax rate calculated as the sum of taxes of the incomes divided by the sum of incomes. Okay? When I run this, this is the average tax of the average income. And so I just execute some more cells here. And then you can see that the average tax rate is actually something like 24% on my data. So don't take this as, actual real world something. It's just, fake data. Anyway. Okay. So we're expecting 24%. And when I execute the whole thing in Python, it takes about 3 seconds to calculate this for the data set of, how many do I have? I actually didn't take the 44 million. I took something like a 20th of that, okay? Just to make it, keep it calculatable during the talk. Okay, so for that number, it takes about 3 seconds to calculate the average tax rate, like the brute force way in Python. Okay, now it reminds me that when you do, when you do measurements on a laptop, don't remember switching off energy management because it messes up your numbers. But this is about what you would expect. It's, it runs long enough to scale up the CPU. So, I'll remember this as the baseline. And then to make things comparable, I have a little function here that tells me, okay, factor 1 is Python, and then I'll have different implementations. I'll go along optimizing this, and I'll have factors to see how this compares to the baseline. Okay, you'll see. So that's a way to implement this in NumPy. How many of you think you understand this code? Get a bit more over time? Yeah, some more? I don't think it's more than a dozen, okay? It's actually kind of straightforward NumPy code. It's not that simple because the problem isn't that well adapted to NumPy. So basically what I do here is I have a long NumPy array with all the incomes in there, one-dimensional array, and I'm masking out the numbers, or masking in them, that fit my current calculation interval. So they're between 54,000 euros and 256,000 euros. Then I apply that formula to them, and I do that for all 4 sections. And then, so basically, I'm spelling out the same formula we had there, just for different parts of the array. Okay, and selecting arrays by the income range, and then doing the calculation. And it's quite wasteful in NumPy because it has to generate intermediate arrays and select stuff and mask out stuff, and it's a bit inefficient, but it's still pretty fast. And when I do this in NumPy, I get the same 24% that we expected, and time it says it's only taken about 60 milliseconds. So that is way faster than what we had so far. How much faster is it? 0.9. So it's already 50 times faster than the Python version. That's NumPy. Okay. NumPy has a second way of doing this. You can take the actual Python implementation that I had, and you can pass it into NumPy and to apply it efficiently to all values in an array. That's called a ufunc. So you convert the Python function into a ufunc, a universal function, which means that you can apply it to the array and it runs on every element, basically. So I want to do that and run time it again. It's actually way slower than the previous implementation. So all the slicing in NumPy is much faster than running a Python function, but it's still faster than the Python implementation. So here I can see it's 4 times faster than the Python version, right? Whereas the NumPy slicing version is still way faster than the Python implementation. Okay, now let's get to Cython. In Cython, I can do the same thing. I can just take this Python implementation that I had and drop it into Cython, compile it there. Done. And when I run this, It actually comes out a bit faster than what we had before, in the Python interpreted version. Still somewhat slow. Okay. 251. Okay, 51. So that is about 70% faster than the Python version. Not too bad, given that we didn't actually do anything. I mean, all we did was take the code, add this line up here, and then it's 20% faster, or 70% faster. That's kind of okay for, how much is it? 8 characters? Okay, I can live with that. But there are ways to make it way faster, and that is by exploiting what the language provides for you. What it does give you is, your code gets compiled to C, so you can use C data types in your code. And that makes it way faster, because especially this kind of calculation can be done entirely in C. It can be left to the CPU rather than the interpreter. That makes it much faster. So the first thing we can do is we can take this function up here, the text calculation function, and we can say, okay, whatever comes in is certainly representable by C double, so that's a safe bet. And what it gets, so then the income variable here will be C double. The whole calculation can actually be done in C. And let's leave it at that for now, and I'll ask Cython to tell me what it thinks about it. And what you can see here is this line actually became plain C. And this sort of, so the calculation in this line is done in C now, just by adding the typing for the argument, right? That's all I did. But the return value is still Python double. I can change that. I can make the return value also C double. And for that, I have to change the signature a tiny bit. I have to tell Cython that this is no longer a plain Python function, but it's actually a C function now, by changing the def into a C def. And now, this will compile the function into a static C function, so really low level. And that allows me to specify the return type. So now it's a function that takes a C double in, C double out, and all the calling will use C calling convention, and then makes it a plain C function. And down here, where I call that function, you can also see that, well, if you scroll a bit, somewhere down here you'll see, let me find it. See, you really don't want to write this code, C code yourself, right? You want a generator for that. I think it's down here, yeah, here. This is calling the calculation function now. Okay, so it's a C function now. Okay, lots of code going on here. Okay, still same result, 24%, but I can make that run even faster because, oh sorry, I'll just show you how fast it is now. Run it once, and we're down to 199 milliseconds, and that's already about 12.5 times faster than the plain compiled Python version, right? Even compiled is already 12 times faster, and compared to the Python version, it's 15 times faster. But I can get even more, even more out of it by, and that is something that Serge just presented in the Python talk. In Cython, you have to unspell, so unpack the loop now, right? Which is, may I say it, Cython now has Python support, which is sponsored by the Python project, contributed by them. And that allows you to also take NumPy code now and compile NumPy code from Cython now by using Python as a backend. Long sentence. Okay, still what I'm doing here now is I'll unroll the loop. I'll turn the kind of nice Python loop into a C-ish loop now by saying for I in range len incomes. And then I'll calculate the total. That's 0, and the tax starts with 0, and the incomes is added up. Actually, I can just make it like this. Keep it a bit more Pythonic. So for income and incomes, total plus equals income, and then the tax adds up by calling the calculate function tax psi of the income, and then return tax by total. Right? I think that's it. Okay, run that. Looks better now. What's wrong here? Okay, total is not adding up properly. So I make sure those are understood. So I declare my variables now. And this is how you declare variables in Cython. The nice thing about it is that typing is optional. So as you've seen before, everything was undeclared and everything was considered a Python object by default. And now when I declare my variables, it'll understand them, but it'll not do the proper operation. Oh, I'm not declaring income. Yes, that's the problem. So double income. And then I can actually leave that out, I think. So I don't have to declare everything. It just gets annoying after a while. Yes, much better. Yeah, and this is still, so you now can see that these lines here, so the calculation is actually done in C now, so native C code, no longer Python interaction in there. And returning the value then does the conversion back into a Python object. Still gives the same result. Good, didn't break anything. How fast is it now? Well, 29 milliseconds, which is way faster than 200. So that gives us a factor of 100 compared to Python now, and 86 compared to the initially compiled Cython version. Okay, so that's much faster. Okay, I can do a bit more. Cython has direct support for NumPy, or for memory buffers. So far, I kept the data in a Python list, but I can also keep it in a NumPy array, which is much more memory efficient. So a Python list has Python objects in there, so there's some object overhead involved. A NumPy array is basically a flat memory space of C data types. And when I take a NumPy array of C doubles, then it's just flat C doubles all the way, which are very fast to process. So when I switch from a Python list to a NumPy array as data structure now, all I have to do in my Cython code is I have to tell Cython what the NumPy array looks like, basically what the memory layout is. And I do that by saying, you can unpack this NumPy array which comes in. You can take it and interpret it as a one-dimensional array of C doubles. Okay? And the way I spell this is like this. Okay? So the incomes array will then be unpacked by Cython into a one-dimensional, so only one colon here. For those who understand NumPy, this will be kind of obvious. If it was two-dimensional, I would say this, three-dimensional like this, so it just goes on like that. So this is one-dimensional, and I'm saying the data type in that array is C double. Okay, kind of straightforward. Okay, I can compile that. That's all fine. Ignore these warnings. Just a demo. And then instead of passing the list into it, I'm taking the NumPy array now as input. Still get the same result. And time it on it says 362 milliseconds, which is surprising because that is somewhat slow. Let me check where that is. No? Cython Up. Oh, come on. Interesting. Okay, my Cython -A is broken somehow. Yeah, that should be fine actually. So I copied it from above. Should be okay from the calculation side. Oh, I think the data size might be bigger now. Did I cut it down at the top? I just run time it again, just to be sure. You never know. Yeah, that's slow. 20. Okay, data size is the same apparently. Okay, yeah, sorry. What it does here, and that's what Cython A shows me, it does the iteration in Python space, which is a stupid thing to do because iterating over the thing in C space is actually much faster. So what I have to do now is make the loop C-ish by doing this. So that's a really plain C loop now. And then x equals income of I. That should be faster. If it compiles, actually incomes of I. Okay, fix it. So, yeah, still the same thing, and now it should actually be faster. Is that clear? What I did was I changed the loop here. So initially it was running over the loop using Python iteration. So it was actually taken the C double in the NumPy array, creating a Python object from it, passing that through the generator into Cython. Python unpacked it into C double again and did the computation with it. So it was actually creating a Python object on each iteration, right, a new one. And by cutting the loop into some C-ish operation, that makes it way faster. So we're down to 11 milliseconds now. Okay, and we're at a factor of 262 now compared to the initial Python version. Okay, so I'll stop here, just get back to this again. A couple of ideas for future features. As I said, we have Python integration now, and I would like to extend that. So it would really be nice to be able to, you know, so we have a more efficient way now to deal with NumPy operations in Cython code, and I think people should start using that. There are also a couple of C++ integration ideas that we have. For example, instead of having a list comprehension in a Python list, you could do the same with a C++ vector. This would be how it looks like. It's probably easy to implement, and that would be a cool new feature. So if you want to contribute, come talk to me on the conference somewhere, or contact me via email. It's certainly something that people would benefit from. Okay, that's it. I brought stickers, so grab some on the way out.